our last section of the semester today, section 6.1 on area between curves. And you'll recognize this applet from when we were finding area beneath a curve between the curve and the x-axis. And that's why we had that g of x in this applet equal to 0. Y equals 0 is the x-axis. So in this section, we're going to change that lower bound from being the x-axis to being a different curve. So I'm going to type in a different curve. Let's do a line. Let's say x minus 3. All right, so now we see the area that's not just between the curve and the x-axis, but the parabola and the line. Here we have the other GeoGebra applet that I have posted in the resources for the week. I've got the same two curves graphed here, the same area shaded between them. I wanted to remind you of those rectangles that we did a long time ago in chapter 5 that eventually led us to the definite integral. I'm going to turn those rectangles on now. Remember, those rectangles were approximating the area under the curve, and then the idea was that we let the number of rectangles go towards infinity. So once there were a bajillion of these, we were calculating basically the exact area underneath the curve. So our definite integral came from these rectangles, and we had that f of x dx came from the height of the function, the y coordinate, and the dx was the width of those rectangles. That dx is still going to be the width of the rectangle, but I want you to pay attention to the height here. So the height of each rectangle is now determined by both functions. It's going to be how high the top function is minus how high the bottom function is, the difference between the two y coordinates. This is what I was getting at with that GeoGebra applet, that we wanted to be able to calculate that area between two curves using a definite integral, and that the height of the rectangle now, instead of just being that function f of x, now it's going to be the top function minus the bottom function. And again, this whole bit is going to represent the height of each one of those little bitty slices between those two curves, and then the dx is still the width. And then we just use a definite integral to go ahead and add up all those tiny little slices to get the exact area. Let's actually give one of these a try. We're going to find the area of the region bounded by f of x and g of x on the interval 1 to 4. And when you're doing these, you do need to do a little bit of curve sketching to be able to tell which graph is on top and which one is on bottom. And some of these problems are going to be very easy and straightforward, and a quick sketch is all we need. Some of them are going to need a much more detailed graph and perhaps a little bit of algebra to work out. So let's draw a quick graph and see if that's going to be good enough for this one. So I've got f of x equals x plus 4, and that's just a line with a y-intercept of 4. So we'll go up to 1, 2, 3, 4, and give myself my y-intercept. And then it's got a slope of 1 at 1x plus 4. So I'm going to go up 1 to 5 and to the right 1. And I'm just going to give myself a few points on this line. So up 1 and to the right 1. All right, so let's draw in a straight line, straight-ish with my pen here. And then let's graph g of x equals 3 minus a half x. If it's easier to think of that as negative 1/2 x plus 3, that's a line with a y-intercept of 3 and a slope of negative 1/2. So we're going to start off at y equals 3 for my y-intercept. And then I'm going to go down 1 and to the right 2. So down 1 and to the right 2. That's going to put me over here at 2, 2. And then we'll just draw the line. All right, and let's just go ahead and label those. This one was the negative 1/2 x plus 3, and this one's the x plus 4. All right, so there's our two graphs, and we want to look at the area between them over the interval 1 to 4. So here's x equals 1, and we'll say 3, 4. So it looks like between those two x coordinates, we have the top curve is always x plus 4, the bottom curve is always negative 1/2 x plus 3. This one's going to be a really straightforward one. We don't need to do anything fancy here. So I'm just going to go ahead and shade that area so we get an idea of what we're doing. So then x equals 4, I'm going to draw kind of a vertical line. So we're talking about this area here. All right, so pretty straightforward. We're going to integrate from 1 to 4, and we're going to do top curve minus bottom curve. So we're going to have our limits going from 1 to 4. Our top curve is x plus 4 minus our bottom curve. So when you subtract the bottom curve, you want to put it in parentheses if it has more than one term to it. And we'll put negative 1/2 x plus 3, or 3 minus a half x, whatever makes you happy. All right, so that's the height of our rectangle. The dx is our width. And we're going to simplify and then find an antiderivative. So let's distribute that negative sign through the parentheses. I've got integral 1 to 4. X plus 4 plus a half x minus 3. All right, so we're going to combine the x and the 1/2 x. So 1 plus a half is 3/2. So I'm going to have 3/2 x. And then our constants, I've got a 4 and a -3. So I've just got +1. All right, so we just need to find an antiderivative. Let me go ahead and clear off a little bit of my slide. All right, so let's find our antiderivative. So the 3/2 is a constant, goes along for the ride. X, we can just add 1 to the exponent, x squared divide by the new exponent. And antiderivative of 1 is going to be x. And then we're going to evaluate all of this from 1 to 4. And again, if it's a little more straightforward, we can turn that evaluation bar into a bracket. All right, so I'm going to simplify a little bit before I plug in. I'm going to make this, let's multiply those 2's together. So this is going to be 3/4 x squared plus x from 1 to 4. All right, so we plug in our top limit minus our bottom limit. So I've got 3/4 times 4 squared plus 4 minus, and I'm going to put a set of parentheses here so I remember to subtract all of it. 3/4 plugging in 1. So 3/4 1 squared plus 1. And let's see what we've got left. So this is 3/4 times 16 plus 4. So I'm going to distribute this subtraction to both terms here. I've got minus 3/4 times 1 and minus 1. So let's see, this is just a bunch of arithmetic, right? The 4 and the 16 here can reduce. So this is going to give me 3 times 4, which is 12. And I had a plus 4 minus 3/4 minus 1. Let's add up all of those integers. So 12 plus 4 gives me 16, minus 1 would give me 15. So I've got 15 minus 3/4. And let's see, let's get a common denominator on that 15. Let's see, 15 times 4 is going to be 60. So I'm going to make this 60 over 4 minus 3 over 4. And I get 57 over 4. Let's go check this on our GeoGebra applet. All right, I've gone ahead and plugged in our two curves. F of x equals x plus 4, and g of x is 3 minus a half x. And a is 1 and b is 4. That's our interval 1 to 4. And they've shaded the area. It looks very similar to what we got in our picture. And it says the area is equal to 14.25. That's the same thing as our 57 divided by 4.